Okay, so let's start today's lecture. So today I can imagine many students already return to their hometown to enjoy their holidays. So, so I mean, it was also same in the other classes. Okay, so based on this one, I mean, before we start, I mean, maybe your major interest is about the evaluation during this course. So based on the teaching plan, in week 6 after the New Year's holiday, you will have a quiz, and then it will be I will assign the 2 hours, but I I expect I'm sure it will be very not spend a long time. So if you finish earlier, then you can leave earlier. Okay. So basically, most of the questions will be not difficult, very basic. I mean, similar to the quiz. Okay. But because I should make a grading, so maybe some questions are somewhat not easy. Okay. Not easy means that it does not take long time. Not the mathematics. I will ask you. For instance, I mean most of questions are multiple choice, but the some of questions will be subjective. So for instance, I can ask you, I didn't decide the question yet, but I can ask you, so explain when Tobin model is necessary, something like that. Then you need to explain it right down there, okay? So something like that. So I mean, it will not be long, short to answer question. And I believe actually the mathematics will not be complex, but anyway, some students can complain, oh, the calculation is too difficult. So I recommend you to bring your calculator for any of your convenience. Okay, and then this is the on-site. Okay, so you should attend the class on-site, especially for the quiz one. Okay, otherwise, I mean, you will not get the score. And one thing for the another assessment, the project presentation, also only 5-minute presentation, and you can just explain, I mean, your work, how it is related with the probability, statistics, or machine learning. So this content is the same as before in my announce in the lecture 1. But the one thing, the deadline is a little bit extended until the end of the week 13. So here, April 3rd, April 19th, on until the Sunday. Okay. Maybe in terms of the project presentation, the Professor Mawei in the second half, he will explain more detail later. Okay. And then any other question about quiz 1? So did you check you should already check homework 1, right? So it's okay, right? It's very, very fundamental level. So maybe similar, but some questions are a little bit more complex. Okay. Any question? I think it normally spends 1 hour. 1 hour is okay. But of course, I mean, if you need more time, I can give you more and more time. Okay. Okay. And assignment 1. Oh, assignment 1 again. The due is the 25. So you should submit your answer about the assignment 1 on the Blackboard. Okay. Okay, so let's review. Today I will first lecture the contents of today, and maybe if I have time, I will briefly review of the other lectures that I have done for review for your quiz 1 or something. Okay. So here, first week you learned about the first week is about the statistics and the probability method is about the basic. And the second week and third week, you learned about the regression and the simultaneous equation models. And week 4 was about the latent variable models, including the structural equation modeling. So one thing here, about especially the week 2 and week 3 and week 4, I lectured some several models. So can someone answer that? What was the common things in those models before? until week 2 and week 4. Regression model, latent class model. What was the common things? Of course, the model are different, but they share the common feature in terms of Y. Yes, continuous. This is the continuous model. Continuous means that continuous, like your salary. Okay, some continuous numbers. So based on this one, I mean, again, this is the general type of the data. So for the data, you can ask, is it general? I cannot say all data format should be like this, but this is the most common general data format. Okay, then how you get this data? It depends on your major. Some of you maybe collected this data from the survey, and some of you maybe collect the data from the experiment. And some of you can also collect the data from the big data, just to use the passively collected data. Or these days, most state-of-art things is that data fusion, integrating multiple sources of the data. Okay. So anyway, so in this case, you can first set up your input data, and then there are some multiple variable x, several variables, and then depending on your research interest, you can choose one of them. You should choose one of them, and then it will be your y, any of them, based on your research interest, research point, and then this will be your title of the PhD thesis normally. So I cannot say this is every discipline, but at least within the FCE, this discipline, including civil engineering, LSGI or BRE or BEEE, this is our general process here. Okay, but here, so based on data, what people normally think that they normally apply the data for the regression model. This is the most basic. But normally, the researchers, we estimate the regression model, just without any further assumption. But in the regression model itself, what is the basic assumption is that our dependent variable y is a continuous. And then the other x, except for y, they should be independent. So this is the basic assumption in the regression model. But of course, in general, in your data set, especially if you use the data fusion, the integrated data, they normally very highly correlated. Okay, so simple regression is not proper for your research, especially if you target the Q1 journal in your field. Okay, so that's why we need some advanced model. So here I lectured some advanced model in terms of the regression and the simultaneous equation models also, and some also latent variable model. Okay, and then based on this in line with this contents, today I will explain more advanced topic. Actually, it's not much advanced, but anyway, compared to the regression model, this is the more specific, special cases. So sometimes your Y data can be count variable or discrete variable. Okay? So based on this one, I will lecture today count data model and the logistic regression. This one especially close to the machine learning classifier. This is the logistic regression is the base of the machine learning classifier in any textbook. Okay, so I can imagine maybe in the second half, the Professor Ma maybe introduce more detail about the logistic regression in terms of the machine learning classifier. Okay, and then another issue is about the discrete outcome models, and then discrete or normal scale data, and so on. Okay? So let's first talking about the count data. So count data means that Y is the count variable. Okay, what is the count number? Integer. Okay, 0, 1, 2, 3, 4, 5, something blah blah blah. Okay, but of course this is the number, so the count means that non-negative. Okay, so This data including discrete variable, non-negative variable, and often skewed. Skewed means that something like this, like a log normal distribution. And the variance frequently increase with the mean, something blah, blah, blah. Okay. So typical count variable, for instance, number of driver route change per year. So we can say 0, 1, 2, 3, 4, 5, something blah, blah, blah. Okay. And then number of trip departure time changes, number of vehicle waiting time. Sorry, not waiting time, the waiting number of accidents, and the number of red light running violation. Anything about the count. Okay. So here, then a question. Oh, we still have a regression model. So why I need to use the specific count data model? Because I mean the linear regression is not proper to here. Why? Because they assume y is the continuous. So sometimes why? Because y is a continuous. So the model, even though they use the count data, they can predict y is about non-count, like a y point 2.7. Count data 2.7 is not proper because it's about the number 1, 2, 3, 4, 5, right? And then it can also predict the negative value, right? So y equal beta x blah blah blah. So negative value is not matched with the count. And then it assumes constant variance. So again, recall the previous lecture. You learned about two estimator, OLS, the ordinal least square, and then the MLE, the maximum likelihood estimator. So in the regression model, when OLS is preferred, you remember? So the errors are assumed to be IID normal, right? In this case, OLS is preferred because the estimator could be unbiased in OLS, but the MLE estimate the beta, the mean of beta is unbiased, but variance of beta can be biased. So this was the core in lecture 2. Okay, in the quiz I can ask you, okay? Okay. And then assume the normality residue. Yeah, this is about the IID normal. Okay. So in the count data, in the regression, this assumption is difficult to be defended. Okay. So question, so what kind of model we can use for the count data? So one of the popular model is the Poisson regression. So if you working on the count data model like traffic safety, and then maybe you heard about this. If your supervisor is Professor Tony C. in CE, then you should have heard about this. Okay, Poisson model is the most popular one to estimate the model for the count data. Okay? So typical count data example, dependent variable, number of accidents, safety area. And then why the name is the Poisson regression? It assumes Poisson distribution. Poisson is the name of the researcher. He found this distribution first. So we can see there Poisson distribution only defined non-negative values. And then it is a little bit skewed left side, right? And then it only predict in the number, non-negative numbers, 0, 1, 2, 3. So it is very proper for the count data. Okay. So here in the reality, many intersection, if we focusing on the number of accidents per year at the intersection, many intersections have a 0 or very few accidents. So left side is skewed. And the events are relatively rare. Therefore, this skewed shape Poisson distribution is a natural starting point. Okay. So this is the Poisson probability mass function there. So P, the probability is Y is the accident, and then exponential, blah, blah, blah. Okay. lambda is the expected number of accident. And then here, in this case, mean and variance are equal in the Poisson distribution. This is the key feature. Okay. And the core idea. So here, the lambda is about the expected number. So we do not model y directly. And then we model the expected value lambda. So in the traffic count model, we normally, the match with y and the x, something like that. But in terms of the traffic count data, actually focusing is the lambda because it's about the count number. Okay, and then it can be function of the fx and y, something like that. Okay. So here, most common link function is that, so here, instead of the y, lambda is kind of the exponential regression. Exponential beta 0, beta x summation, blah, blah, blah. Okay. And then if we translated log sum for the both side, and then like this, the y part is the logarithmic lambda, and then other part is about the simple linear regression. So this logarithmic function is a non-negative function, so it ensures lambda should be a non-negative for the all variable of the x. Okay. And then interpretation of this variable in Poisson regression. So many times, we normally, so far, what you learned is that how to interpret the beta in the regression model. But in reality, many times, many contexts, the beta interpretation of beta is mainly limited. So for better practical meaning is that it's about policy recommendation or some maybe some research context. It can be directly suggestion how to improve your experiment, something like that. We normally use the elasticity and the pseudo elasticity and the marginal effect we can calculate. So here, using the beta model is the exponential lambda. So here, based on this one, in the Poisson distribution, lambda is the exponential beta multiply x. So in this case, in the Poisson regression model, beta only tells change in log lambda. So effect size depending on the current value of the x, right? So it is difficult to compare importance across the variable. So now this one is only the relationship beta and lambda. So x is not be related. So in this case, we need to standardize or percentage-based or unit-based measures. Okay. So in this case, we normally use the elasticity. This is the more economic concept. So elasticity means that the percent change in expected count caused by 1% change in the explanatory variable x. So x become x. Then here is the lambda. This is the elasticity. Okay, so how to calculate it? We normally percent change, but if we say the 1% is very small change, then we can use the concept of the derivation. Okay, so if you derivate about the Poisson regression function, the elasticity for the x in terms of lambda is very simply the beta multiply x. So it is very easy to be calculated. Okay, so normally in the Poisson regression model, we use the elasticity value. So beta is fixed by estimation and x is depending on your data. So we can just sum and then make an average. Okay. So here, for instance, let's say based on the elasticity, So something like that. And then we get the average elastic value. For instance, plus 0.65. So it means that expected count will be increased by 0.65% when the 1% change in X. So in this case, we say it's a positive because positive value and inelastic. Inelastic. So you learned that last time. Inelastic means that elasticity is lower than 1. Okay. And 1.40, same positive elastic. Elastic means that 1. I lectured in lecture 2, right? And then it's on negative, and then negative and strong negative, and then minus 2 point, very elastic. Okay. So here, but still, I mean, okay, I can calculate the elasticity for the Poisson distribution. But still, I mean, actually, this is not only the problem within the Poisson regression model. This is for the general problem in the regression family models. Any regression model also suffer the similar problem. So here is, so in this case, elasticity applies only to the continuous variable. Why? Because the definition itself 1% change in the X, right? X become 1.X. But as you learned week 2 and week 3, you learned about the category variable, right? So, for instance, in this case, some example. I mean, this continuous variable, I mean, lane width and the shoulder width and distance to load size object. This is the number, continuous variable. So sorry, the lane width is 5 meter. Then 1% change means that 505 meter. This is okay for the elasticity. But the problem is that category variable, dummy variable is not okay. So for instance, you estimate the model with the category variable, female. For the gender, female, 1, male, 0. Then for this variable gender, concept of elasticity does not mean anything, right? 1 or 0 is not about the value. It's just an indicator, right? So in this case, we can calculate the elasticity, of course, same way, but the conceptually is not valid. Okay. So then in this case, in your model, what you can do? So to solve this problem, we normally use the pseudo elasticity. So if you're working on some statistical analysis, I mean, then you can find journals in your domain. Then some papers using the pseudo elasticity to analyze your data. So in this case, you can think that, oh, pseudo elasticity, category variable. Okay, not continuous variable. Okay, dummy variable is also kind of the categorical variable. Okay? So let's say, okay, when x1, 0 or 1 here, this is the male and this is the female. And then we can calculate the pseudo elasticity. I did not include how to derive it, but if you're interested, you can check more detail about the mathematical derivation. Okay, so in the Poisson distribution, it can be defined like this. Okay, then interpretation. Given the approximate percentage change in expected count when the indicator change from 0 to 1. This is the definition. Okay, so for instance, beta estimated for gender. So for the gender, beta is the minus 0.45. It means that if the male, no change. But if it is the female, the y will be decreasing as much as 0.45. Okay. In this case, we can calculate the pseudo elasticity, exponential, blah, blah, blah. And then we can say the change, this one is the about 36% decreasing. So it means that presence of the feature reduce the expected count. If it is the male, y, the count about the y will be decreasing as much as 36.2%. Any question? So quiz level, what I can ask you, even though we have a elasticity. What is the limitation of elasticity? And then what is the solution? What is the solution index? And then you can say, okay, the elasticity is difficult to be applied to the non-continuous variable. And then we can use the pseudo elasticity. That will be the answer. So quiz will be like this level. Okay. Okay, then last one is the marginal effect. Yeah. So this is the another useful interpretation. So marginal effect means that much simpler, absolute change in expected count. So it's just about derivation. Okay, and then if you derivation. So here, if you derive lambda in terms of the x, then you can derive exponential blah 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 dxk something like that. Then it will be like this. So this is just about the derivation of the exponential function, the rule of the derivation of exponential function. Okay, beta will become outside in terms of the xik. Okay. And then interpretation, average marginal effect means that how much lambda changes in absolute unit. Okay. When xk is increased, when x increased by 1 unit, how much it changed by in the lambda. Okay. So it's very intuitive for integer or small scale variables. And then this is the comparison for the elasticity, pseudo elasticity, and the marginal effect. So what it measure? Elasticity percent change in lambda for the 1% change in x. And then pseudo elasticity approximately percent change when dummy variable, categorical variable changing. And the marginal effect change in lambda for the 1 unit change in x, just for the derivation. Okay. Then in the literature, what we normally use in the Q1 journals, elasticity, very common. Because normally our data is about the continuous variable. But sometimes still also the pseudo elasticity when your data is about the categorical variable. A marginal effect not much common as much as elasticity, but still it can be useful. Okay. So here, so I need to analyze my data, then which one I need to choose? How can I decide it? So normally for the elasticity, so most common choice in literature, elasticity or pseudo elasticity. But in my experience, elasticity is much better. So why this is the unit-free for the continuous variable? And then it allow comparison across variable with a very different scale. Okay? But still marginal effect is useful when the policy interest is absolute number or of accuracy reduced, or anything about the categorical variable. It depends on your research purpose. And when the variable is integer and small. So integer is a kind of the categorical variable. Okay. So this is about the Poisson models. And then, of course, I mean, in the literature, if you use the count data and then you are targeting the Q1 journal, then the Poisson regression model is basic. I mean, it's not how to say the state of art. It's a classic, but not the state of art. So based on this one, the academic researchers, they develop the model more and more better advanced modeling. So for instance, it's about the truncated Poisson model. So truncated Poisson model, I didn't include the detail in this lecture, but you can see here, in the Poisson distribution model here, I mean, one feature of the Poisson distribution. Normally, it starts from 0, non-negative value. But depending on your data, I don't know what is your data, but some data could be started from 4 or started from 10, depending on your data. You don't know. But in this case, still Poisson distribution is not much fit. So in this case, we cut the distribution arbitrarily and then make a fitting with a truncated distribution. Okay, so truncated means that cut off. So we arbitrarily cut the value. So this is the truncated distribution. Is one of the hot issue in the probability studies. Okay, even the normal distribution, I mean not the Poisson distribution, normal distribution, it can be positive or negative, right? In this case, some researchers, they use the truncated normal distribution to better fitting for their data. Okay, and then also some use the negative bio. Some researchers, they apply negative binomial distribution instead of the Poisson distribution. Also, zero inflated Poisson and the negative binomial distribution also. So they become now more and more complex distribution to fitting their data. Okay, so this is about the Poisson regression model. So any question here? Okay, so Poisson distribution is quite a common issue, but data is very specific. I mean, your data should be about count. The Y should be about the count. Okay? And then let's continue. And then next issue is about the logistic regression. Okay, logistic regression here maybe as I introduced in this lecture today, I mean, logistic regression is close to the machine learning classifier. So maybe if you are plan to use the machine learning classifiers to analyze your data, maybe you should start from the logistic regression as a classifier. Okay. So also for the new model, always the question why it is necessary, right? So always, if you have a data, the basic is the linear regression. Why? This is the very most easy, most convenience. Every software, it supports the linear regression model. But here, I mean, many times the linear regression has been limited. Why? Because of the estimator issue. So why not? OLS estimator for the regression is not suitable for all cases. Linear regression model assume dependent variable is continuous. Y is continuous. And then many real world outcome are not continuous. Sometimes it can be discreted and sometimes it can be categorical. So Poisson model is one of the case for the counted data. But Poisson model is a very specific only for the count data model. If your Y is count variable, then it's suitable. But also it can be ordinal rankings. I ask you, for instance, for the MTR in Hong Kong, how much you satisfied? And then number 1 is the very satisfied. Number 2, satisfied. Number 3, neutral. Number 4, not satisfied. And number 5, strongly not satisfied, something like that. In this case, the answer is ordering. And sometimes it can be binary outcome, something like that. Your Y is that your Y can be gender. If you are male, is 0, and female is 1, right? So in this case, I mean, especially the logistic regression about this case, the outcomes, binary outcomes, yes or no, 1 or 0, success or failure. So binary outcome itself means that clustering, right? 1 or 0, 2 area, which area you are included. Therefore, it is about classifier. the group, the dividing the group. Okay, so in this case, the goal of the logistic regression is that identify a well-fitting model that describes the relationship between binary dependent variable, okay, and then set of the independent and explanatory variable. Okay. So it is same overall goal as a linear regression, but for the binary outcomes. Okay. And the independent variable are assumed to directly, indirectly influence to the outcome. Okay. And then this is the comparison. So for the logistic regression, of course, I mean in this lecture, for the ease of understanding, I will only talking about binary outcomes for the logistic regression. But of course, I mean, if you have a multiple category, group 1, group 2, group 3, something like that, then of course, advanced logistic regression model can be applied. So therefore, it can be directly close to the machine learning classifier. Okay. So here, this is the comparison between linear regression and the logistic regression. So point is here, dependent variable, always. Then what is the other point? Equation. Others are very close, very same. But here, y is different. In this case, y is not about 0 or 1 directly. So point in the logistic regression about that, it used the concept of the odds instead of the probability. Okay. So here, so what you need to understand is that you should understand about the difference between probability and the odds. Okay, so probability, I mean, I don't need to explain, right? But odds concept is a little bit new. I mean, so it's about the ratio of the probability to event of non-event. So if it is probability 1, if the probability is 0.1, it means that this one is included in the also denominator, right? But in the odds is not included, except for 1. Right? So, so then what I can ask you during the quiz 1, okay? So, okay, now I have a probability 7.3. This is the P, okay? Then what is the odds there? Very simple, right? So what is the odds? Okay, it's very easy, right? Okay. So this is the difference between probability and odds. I mean, here the upper side is same, but only the denominator. This one is included in probability. The upper side is including in the denominator, but in the odds, upper side is not including in the denominator. So their value is different. So in this case, if the probability is 0.1, then odds is that 1 per 9. Okay. So interpretation 1 in 9. Okay. So this is the example. So actually but anyway, I mean, so it's about the derivation, but maybe not in this class. So in this case, P01, the odds is the 1 to 9. That's all. Okay. So here, now they use the odds as a y in the logistic regression. Okay. So same in the machine learning classifier, logistic regression classifier, same. They use the odds instead of the P. So this is the direct relationship between P and O. P equal very direct. What is the one here? So here odds level here. That's all. Okay. So same as a p, and then odds is 1 to infinity. That's all. So again, odds ratio comparing two event odd ratio, odd of event y and odd of the event b, not a, not including a. Okay. So here there are two events. So in this case, real and classic odd is 1 to 9. And then stepwise classic odd 1 to 4. In this case, odds ratio. Okay, so I mean, let's assume. So let's think about the accident rate. Okay. So we have a two groups, real and classic, and then stepwise crash. And then for the odds, real world crash is the 1 to 9, 1 by 9. And then stepwise crash is 1 by 4. In this case, for the logistic regression, to decide that percentage for the each class, we normally use the odd ratio. So it just divide the odds between two groups. Okay? So interpretation means that the odds of the real and crash C are 4 to 9 times the odds of the stepwise crash. So it's just ratio. Okay. So here, any question about the odds? Okay, maybe you learned about this before. No, okay. But I can imagine because here, if you are in FCE, you learned about basic statistics before, right? Okay. Okay, but in your master, maybe you no. Okay, I see. Because today I have a meeting with another lecturer for the part 2. And then he basically assumed that you have very strong mathematical ability. So I said, I think I'm not sure. And then because when we're talking about the assignment 1, he believes it's too easy. So I think it's enough. So, but okay. I see. Okay. I mean, okay. So I mean, anyway, I mean, this is about the odds. Okay. And then in the logistic regression, I mean, this will appear in the also machine learning in part 2. And then normally we use the log odds instead of logs. So I mean, issue is very, very similar. So you remember in the the likelihood MLE, the name itself is the maximum likelihood. But I lecture that we normally use the log likelihood instead of the likelihood, right? Do you remember why? I show you using Excel at the time in the lecture. This is more practical reason actually. So we normally take a logarithm value instead of the low value. Yes. Based on the multiplication, 0.1 multiply 0.2, 0.3, then number is very, very small. So if we use a statistical software, then software makes some error. They cannot calculate it. But what good things is that the pi in the log pi means that multiply. Then, I mean, mathematical rule is that it becomes sigma. So it can be increasing. Therefore, we prefer log likelihood value. Okay, similarly, you can imagine. So why we use the log odds instead of logs? Because of the computational issue. Okay. So I mean now, this is the very general problem. So number itself is enough for the odds ratio. But in the real data, maybe this one is very small. Something like that. Something like that. And this one is also very, very small. Then the calculation sometimes is not easy by the software. And then taking the log can be more beneficial in terms of the calculation, practicalism. So in this case, also we use the log oz. Okay. And then this is the shape of the log oz. So here you can see where it is. Here. So in this case, based on the definition, oz have a value from 0 to infinity. Okay, then we can say when we draw our graph, I mean, anyway, the maximum is 1 because probability is the maximum value. So here, sorry, maybe I can show here. So in this case, if we do not use oz, then value will be something like that, because it's the upper bound is the maximum there. Okay, but so in this case, but instead log oz, if we draw it very how to say beautiful S shape, we normally call it S shape function. Okay, so some people ask why the name? I mean, okay, so I mean linear regression, linear, we can understand it, right? So I mean it's not difficult. This is just linear, right? But logistic regression, logistic, what is the logistic? I mean, this is the first question, right? Also, in my during my early days, I mean, when I also studied the logistic regression, what is the always difficult is that why the name is the logistic regression? Logistic. When I heard about the name, I can imagine logistics, right? But it's not actually logistics. So if you study more detail, because by another researcher, this function is called the logistic. Also, sometimes if you use the logistic, then sometimes we call it logit. Okay, so why the logistic regression? Because they use the log oz, therefore this shape function they use. So logistic name is the logistic regression. Okay, so if you have an interest, maybe you can find some. Logistics. Sometimes here many people explain this, and then based on this, I mean the why, because of this one logistic function, okay, from 0 to 1. This feature is very unique in logistic model. So maybe it's out of this lecture, but many times this called softmax in machine learning. Maybe you will learn in the part 2. And then sometimes it's I forgot the name, sigmoid, something like that. So this function they directly use in machine learning model. Therefore, the many textbook, all the textbook, logistic regression is the basic classifier of the machine learning. Okay? And then, of course, I mean the logistic regression as a classifier. I mean, for instance, like this, between 0 and 1, the model classify. If it is below than 0.5, then this area, and if it is higher for the 0.5 and this class, sorry. Maybe I should capture. Maybe I don't know. But anyway, so here, based on this one, what we can do, as you can say here, we have a two level. For instance, this is the male. This is the female. Okay. So if it is lower than 0.5, we say, I mean, just for example, I mean, not real. We say, oh, this person is more classified to the male. Or if it is higher, then this person is more classified to the female. I mean, just for example. Okay. So in this case, we can classify the other people. This one is a male or female, male or female. So it can be classifier. But of course, I mean, logistic regression itself has some limitation. So there are more and more advanced machine learning classifiers. Okay. So what is the most limitation is that associate the symmetric symmetric associate. But normally it can be asymmetric. So I mean, many statistical issue always. I mean, for all the statistical modeling, what is the general issue is that how can I develop the mathematical model, more generalized model, and then what is the new finding in using my data analysis, asymmetric rather than symmetric, something like that. Because classical model we normally assume symmetry, and then very simple. Okay. Okay. And then why logistic is very popular in the classified models? Because mathematically very convenient, very easy. Okay. So summary: probability, odds, and odds ratio. What is the logistic here is that we use the log odds for the logistic regression model. This is just the point. Okay. So in this case, range of the x become -infinity to infinity, and then symmetry around 5. So symmetry S shape. This is very, very, very beneficial for the computation. Okay. And then very, very common. I mean, this is the dominant actually, log odds. So we normally use it logit model. Okay. Why logit? They use the logistic shape here, S shape. Okay. Logit appear many times, many models. But you can imagine why the name is the logit. Logit for the choice modeling, logit for the regression model. Why they call the logit this shape? Okay. So the dependent variable y in the logistic regression, I mean dummy coding, I mean the female, male, accuracy occurred, no accuracy. I mean anything, pavement deteriorated or not deteriorated, and the CPELD used or not, anything. Okay. So core idea modeling the log odds here is that logit pi equal logarithmic pi divided by 1 minus pi. So it means that here. So this one means that log odds. Okay. So logit p is the natural log of the odds, log odds. Then the right hand side is linear in parameters like this. And then beta intercept and the coefficient, I mean same. So here, of course, based on the log odds, we can translate it into the probability, something like that anyway. So in this case, this function, it can be pi, and then this function, it can be exponential, blah, 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 1 divided by this. Okay. So in the literature, I mean, in the academic papers, in the journals, I mean, estimation of the logistic model based on the log odds. But once you find the paper, then many people also use this term. 1 divided by 1 plus exponential beta x, blah, blah, blah. Any questions so far? It's not difficult, right? So far. Okay, then let's take a 10-minute break, then I will continue.
about the course project questions. Because I'm from the construction management field, so my subject is not very like strongly related to like probability and statistics, but loosely related.
Anything, just emphasize the part. It's okay.
Okay.
So let me know the big picture, big description about your PhD work, and then you don't need to explain all. I mean, just focusing on this part. I need this one.
Yeah.
That's all.
My concern is like they'd be like some too low level like movement, because you know the problem in construction management is all about some like process simulations and about this activity duration, like a normal distribution or something, some special distribution, some kind of like that.
Maybe, I mean, you can just think about that. I mean, how to say, you just this is your plan, but based on the you are learning in this class, maybe you can think about this way. That is, I think, enough. I mean,
Sure.
who is your supervisor?
That's a Lumi.
Huh?
From BRE.
BRE. Okay. Because in CE, we also have some professor in CM. Okay.
And do I necessarily have to include like machine learning?
No. Anything about the, I mean,
Just about one
of them. Yes.
Okay.
I mean,
Not
it's
all
not
of
mandatory.
them.
Yes.
Okay.
I mean, our purpose is that just
Okay.
yeah. So not don't need to be. I mean, make it complex.
Okay.
Okay. Oh.
You give the like t-test paper or
If it is necessary, I will provide all. Okay, so Okay, so let's start the second session. And then based on the learning of the laws, let's continue. So again, this logic function is about the symmetric S shape. So it is approximately linear in the middle range. Here is not linear, but almost linear here. And then 0, 0, 0, and 1 is almost 0. So it means that here, compared to the max function, so what people normally want here like that, some 0, 0, 1. So for the classify, what people normally want, ideally, this function. I mean, here is a 0. 0 is classically 0. And 1 based on X area. Here is what? Here is 0. And here is 1. And in the middle is a linearly varying. This is the ideal, conceptually ideal case. But this is the conceptually ideal. But practically, what is the problem is that this is the, how to say, derivation is not possible. Right? Then estimating beta have some problem normally. So I'm not remember, because normally MLE or some other estimators normally they estimate the beta based on the derivation. Do you remember in week lecture 2, I remember, or lecture 3? So in the regression model, when we using MLE, how we estimate the beta, even the OLS, we estimate the, equal to 0. Do you remember? Maybe I will review. I mean, at the end of this lecture. So anyway, I mean, so what my point is that, I mean, this is the idea, but in this case, what you just need to know, estimate beta is not possible. Why? This point is not underivational. Derivation is not allowed, right? It's not it's how to say, it's not soft, right? So instead, people prefer logit. Why? They have a core property similarly here. Here, not exactly 0. It's a very, very small positive value. But here, almost 0. Here is not exactly 1, but very close to 1, right? So very similar. And the middle part, of course, is a little bit flexible, but here is almost linear, around 0.5. So this is the very, very effective representation, approximation of this function. So here, this is very flexible to estimate the beta. So statistical person, they prefer it. So they more use the logistic function. Okay, so just for the tip in practical reason. Okay, so this is about it. Make extreme prediction difficult, realistic, most by binary phenomena. Okay, for derivation is possible, and here is the 1, and here is 0, and the middle is a little bit changing, increasing. Okay. So here, so now using the logistic regression model, how we can interpreting the 1 unit change. So effect of the 1 unit change in X in the O's form. When X is increased by 1 unit, O's divided by O's old exponential beta. It means that X plus 1, then O's X become exponential beta X multiply O's Xi. Okay, so very, very proportional. Okay. So exponential beta is called the odd ratio associated with the 1 unit increase in X. So it's very convenient to make an interpretation. So odds ratio in practical interpretation, if exponential beta is larger than 1, and then we say odds is increasing. It means that, for instance, odds ratio is 2.3. It means that odds increase by 130%, 1 plus 1.3. So again, what it means, odds increase means that when x become x plus 1, odds increase. Okay? Odds when x is increasing x become x to 1. Okay, 1, I mean no change in the odds, and then lower than 1, odds is decreasing, and the 0 very strong positive effects, and then something blah blah blah. Okay. So summary, from model to interpretation, model log odds, also called the logit model, as a linear function of x, logit p blah blah blah, and then estimate the beta using MLE. So question, I mean, so far I lecture several models, but basically, except for the linear regression model, most of model use the maximum likelihood estimator as a basic. Of course, I mean, they can use a more advanced estimator. So why not OLS here? Why OLS is difficult to use here? It means that why OLS is preferred in the linear regression model. Same question before. Why? Because IID normal for the error term is not difficult to defend here. So MLE is more flexible. But there are also more flexible estimator like a Bayesian estimator, something like that. Okay. And then convert to the probability using logistic regression here, something like this, 1 divided by blah, blah, blah. And then exponential beta I after estimation, exponential beta I is the multiplicative change in odds for the 1 unit increase in the x. Okay, this is the summary about the logistic regression. And then as I emphasized in the lecture, logistic regression, I'm not sure, but maybe it should be appear in the part 2 when the machine learning model. So logistic regression is a core supervised machine learning algorithm. What is the supervised machine learning means that what is the supervised? I mean, it will be appear in like part 2 in this class, okay? And then specifically for the classification test. So logistic regression is under linear model in machine learning model, and then it bridges statistics to the machine learning model. And the relationship means that part of the logistic regression, it can be part of the supervised learning. It requires labeled data to a training. So in machine learning model, you will learn about the training data and the test data, something blah, blah, blah. Okay. And the probabilistic model outputs probability, the y value, not y, sorry. The probability is allowing the threshold-based decision, like a 0.5, which here where they more likely to be included. Okay, and then the foundation for advanced machine learning models serve the baseline model. So I mean, once they talking about the machine learning classifier in any textbook, they first starting from the logistic regression. So for instance, the most famous machine learning textbook maybe if your work is deeply included in the machine learning, this textbook is the most famous one in the world. I mean, not only engineering, also the social science, whatever. This textbook is the bishop. This person is the famous for this textbook. But in this case, you can find any here the contents there. Contents. Can I see the contents? No. Eh? Oh, I cannot find the contents there. So, maybe. No. As E. Maybe no. But anyway, also this text in this textbook, also the basic is always the logistic regression. Okay. And then how logistic regression work in the machine learning pipelines, steps in the machine learning flow, workflow, data collection, and the pre-processing, gather labeled data, handle missing values, scale feature, blah, 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 and the model training, fit the model using algorithms, and then evaluation, metrics like accuracy, precision, recall. I mean, this will be appear in the second part in this class, and the prediction. So compared to the other machine learning algorithms, just for your knowledge, what is the benefit of the logistic regression? Why it is always basic classifier in the machine learning model? Interpretability. This is the very disadvantage in the machine learning model. And then very simple. Therefore, training is very fast. So it will appear in part 2, maybe. And then let's move to the discrete outcome models. Okay. So discrete outcome models, what you can say, I think you can also think about the model choice. So for instance, in this morning, to come to the campus, which transportation mode you use? Someone maybe use walk. Someone may use the, not train, MTR here. MTR. Someone use the bus. Of course, someone can use also taxi. Okay. So I can ask you, which transportation mode you use today to come to campus? And then my topic is about the mode choice behavior. Then in this case, this one is the my y, dependent variable. So you can see here, walk, MTR, bus, taxi is not about the number, right? They are independent. So here, discrete. What discrete means? That discrete is new words. So what it means? Independent. Okay, they are independent, not as a single number. So in this case, the question how we can model it. So this is about discrete outcome model. Okay, so starting point same. I mean same as a regression model. Beta x, beta 0, beta 1 x1, beta 2 x2, blah blah blah. And then of course there are some error term. And then one different thing is that t is not just like a number. It can be sometimes for the index. For instance, in this example, for your mode choice, walk is 1, MTR 2, bus 3, taxi 4. So in this case, we can make a data as a y equal 1, 2, 3, 4. But 1, 2, 3, 4, it does not meaning it's as a general number. Okay, we can treat it as a discrete number. Okay. And then here, in this case, we can define. So for the I walk, let's just assume walk and not walk. So for the simplification, let's talking about MTR and the bus. Which transportation mode you want to take to go to a city center, for instance? Then we say that probability choose MTR because T, any index for the MTR is larger than bus. This is the basic assumption. So probability that its index value, we don't know, is a T, is the highest among other one, bus. Okay? And this is the core idea based on the discrete choice and the multinomial models. Okay? And then defining probability. So here, this is about Ti. and then this is about Tj. So Pi equal. But based on this one, it can be beta xi plus epsilon, beta x plus epsilon, blah, blah, like this. And then this one, we can arrange it like this. So the point here is that this one is the observed value. Beta can be estimated and x is observed. So we can calculate it. But here, it depends on the difference in epsilon. So mathematically, it is a little bit more complex because epsilon itself is about the distribution. So epsilon j minus epsilon I means that the difference between two distribution minus distribution. So it's not a simple word, simple number. Okay. So here, then the next question is that what is the error distribution here? What kind of distribution can be used? So for the error, normally what we prefer is that normal distribution. So even in the regression model, we assume normal distribution. So why? So in the quiz, I can ask you. So in the general statistical modeling, for the error, why they normally assume, why they normally prefer normal distribution for the error term? Any answer? I lectured, maybe it's also week 3 or week 2. No one. Do you remember central extreme theorem? I lecture week 2. I can imagine. This is the basic in the. No, central. Maybe find it my lecture. Sorry, central limit theorem. Here. What it means that here, if we have any random number, and then it occurs extremely long time. I mean, many observations, many error, many events. But anyway, if we have a random number generation, and then we repeat it forever, then mathematically it follows the normal distribution. So this is called the central limit theorem. So I lectured it in the lecture 2. Here, Y approximately normal, the central limit theorem. Okay, some random number. So error, we don't know what happened there. For this error, regression model or any other statistical model, the error itself is about that the unobserved part. So the unobserved part is not. I mean, no one knows, right? For the observation, error may be different, but anyway, if the error we collect many of error in the real data, then the error will be follow a certain normal distribution. This is the central limit theorem. Okay. So based on this one, normally the researchers in statistics and probability, they normally assume the error terms follow the normal distribution. And then if we error follow the normal distribution, we assume that we called it as a probit model. Okay. And then if we this discrete outcome, if we assume that error term follow a Gumbel distribution, we called it logit. So logit appear again, right? So even you don't understand exactly, but you can assume, oh, logit model, this function appear again. Okay. So here, and then before we go to the detail, we first talking about the concept of the binary and the multinomial. So binary means that two possible outcome. Okay, and then two possible outcome. Actually, this is quite closely related to the logistic regression. Right? In the logistic regression, we assume y is the binomial, y is the binary, 0 or 1. So here is same. The binary in the discrete outcome models equal the binary means that the two possible outcome is a binary. Multinomial, 3 or more. Okay. And then important point. So before we go to there, if your choice, mode choice is between bus and MTR, only 2, then this is the binary. And then if you add maybe taxi here, become 3 or more, then multinomial. Okay. And the derivation and computational complexity differ significantly. And the binary case, closed form solution, blah, blah, blah. And then let's talking about one by one. So probing model, discrete outcome model, what is the point? I mean, let's talking about point by point. Discrete outcome models, there are 2 points. I mean, for the quiz. So in the probing discrete outcome models, what is the assumption of the error distribution? Normal. And the discrete outcome models, for the logit model, what is the assumption of the error distribution? Gumbel. Second point, as I told you, I mean, early days researchers prefer the normal distribution assumption for the error in terms of the central limit theorem. But normally in reality, logit is preferred than probit, even though the central limit theorem. Why? This is what I explain now. Simply because probit computational issue. Okay. So for the computational issue here, I mean, core assumption, disturbance of the error term is the normal. So simplify normal minus normal equal to normal. Okay. And the difference of the two normal variable is also normally distributed. And the binary probing model, so this is the blah, 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 something like that. This is the formulation. And then calculation, I mean, this part is mathematics, so it's not difficult to calculate in software. But problem is here. So error 1 minus error 2 follow a certain normal distribution. And then to calculate the probability, we calculate the value of the CDF. Okay, CDF means the cumulative distribution function, PDF, CDF, right? I explained in the week 1. Okay, so here also same. I mean, you don't need to remember the formulation itself. But anyway, for the calculation of P1, we need to calculate CDF, the cumulative distribution function for the normal distribution. But point here is that, sorry. So this is the CDF for the normal. So point here is that here officially, I mean, mathematically, CDF of the normal distribution, including integral. So integral means that integral from minus infinity to a certain value x. Okay, so integral I mean, for the integral, maybe you have experience in your high school. I mean, for the integral, we cannot simply calculate the number, right? We should integral for the every x. I mean, the integral again. So in this case, computation is not easy. I cannot say it's not possible, but it's not easy. So this is the classical issue in the normal distribution. So in this case, we normally use the numerically calculate the approximation. So because why? Because here, for instance, this is the function. Integral means that this area calculation, right? If the integral is simple, we can do. But normally, if integral, I mean, this function is complex and complex more, then integral is not possible. So the software cannot solve it. So normally people use the approximation or numerical. So numerical issue here, especially, I mean, binary case is okay. Normally it's okay. It's possible. It's not easy, but it's possible. But the multinomial case, if the outcome is more than 3 levels, then not possible, almost not possible. So in this case, integral, if function, probability function is including the integral, we called it open form. What it means, why it is open? In the integral form, here is the minus infinity, open, right? If it is a certain number, x minus 1, for instance, we can easily calculate it in integral mathematically, right? But the infinity, no possible. So we call it open form. But same manner, if it is a certain number, x minus 1, then what can be the name? Closed form. Okay, closed form, therefore, very easy to calculate. Software can calculate it very, very quickly. But open form software may be calculated, but the time will be very, very long to calculate this integral. Okay? So in the probing model, especially the multinomial case, no closed form expression for the probability. So open form. And then probability involves the multivariate normal integrals. I mean, integral here. So what is the problem? Integral is okay, but here the problem is the minus infinity. Then the software is run out. I mean, they have some problem. And then evaluation requires numerical integration. So numerical integration is okay, but you can imagine what is the numerical integration? It means that have you heard the Gaussian algorithm or some statistical issue before? Gaussian method. So what it means that the integral this area. I want to calculate this. Then this is the y equal fx. Then this is the certain point. Let's say. Then mathematically, how we calculate this area? Integral minus infinity x1 and then fx means. This is the what we do. But if it is easy to integral, it's okay. You can calculate still. But sometimes, sometimes some function is very complex, then integral is not possible. Then we call it Gaussian method because Gauss developed the method. How we can do normally to calculate it piecewise. Linear. maybe my rule is not good, but piecewise. Then we can calculate this area, this area, this area, this area, and then sum. But still, I mean, this is called the numerical integration. Numerical. Numerical is almost like a piecewise. I mean, this is the general in statistical modeling. So for the integral, we say we need some several piecewise linear function, and then calculate it. Then what is the problem? Of course, the academic society is not preferred. Why? I mean, they similar, but they are not exactly same as math. But why people still use the numerical integration? Because no other method, no other better method. So here, I mean, this problem, open form issue, integral issue, especially more and more bigger, especially number of outcomes is very large. If you, I mean, if your y is about mode choice, bus and metro, it's okay. Binary situation, only two, not difficult. But here walk, taxi, what others? Ferry. As more and more number, calculation more and more difficult. Then it's not possible. So early days, I mean, very, very long time ago, around the 1950s, by 1950s, the researchers, mathematicians, they try to use the probing model because normal distribution is more realistic based on the central limit theorem. Central limit theorem. But it's not possible. Integral problem. Many people try to get some solution for the integral, but not easy. Then what they do, after that, what they do, they try to alternative model, alternative assumption about the error. So what is the solution? Logit here. Okay. So logit, what they assume? Campbell distribution instead of normal. So Campbell, if you find the Campbell distribution, the distribution is something like this. So it's not, of course, I mean, it's not exactly same, but you can see the PDF, the shape itself is similar to normal, right? The Gaussian bell shape, the single peak there. So researchers find that. So if we assume the Campbell distribution, then probability is the closed form. So where it is. So therefore, it is very easy to be calculated. So these days, for the discrete outcome models, logit is more popular than probit. So many people basically start from the logit. Okay. So logit model has a closed form. And the multinomial probit open form. This is the actually practical reason for the data analysis. Okay, so here is the mathematical expression and about the Campbell distribution. So here, this is the expression of the probability. So here you can compare from the probability of the probit here. Here, this is the open form, but this is just a closed form. No integral here, just exponential. So it is very easy to be calculated. Then question, I assume Campbell distribution, but why the name is the Campbell? Sorry, why the name is logit? You say that logit is like this S-shaped function. you said this is the logit, right? This SGA function is logit. Then we assume Campbell distribution. Why the name is the logit? Campbell logit is not matched because they are probability function here. Probability function here is looks exactly logit function here. Okay, same function, same shape of the function. Only the x-axis is different. Okay. Therefore, logistic regression model, it is also called the logit model, and the discrete outcome model, it is also called the logit model. So many times, I mean, it can make researchers too confused because they use the same name, but the meaning itself is a little bit slightly different. Their x-axis value is different, and we can see even the logit model, because as I told you here, the shape of the logit Campbell distribution is similar to the normal distribution. Their probability function shape is also similar. So they say, okay, probability result may be not much different with the logit. So logit used. Logit is preferred. Okay. So comparison, logit and probit. I mean, no others. This is the discrete outcome models. So just two things remember. Okay. So for instance, multinomial probit, normal distribution. Error for the normal distribution. Multinomial logit, Campbell distribution for the error term. Okay. And then why logit is preferred to the probit? Because of closed form. Here. No closed form is called open form. I mean, in this class, that's enough. 2 points is enough. Okay. And then other detail, if you are more interested, you can find more textbook about this. Okay. Maybe it's too broad issue, but still, I mean, the discrete outcome models, also called the discrete choice model. What is the issue? So we have a logit model, that's all. But actually more issue about here. Logit model is not, it assumes error terms follow a Campbell distribution, but not exact. I mean, Campbell distribution is okay, but more IID. IID, you know what it is? I mean, the identical and independent distribution of the errors. But this assumption may be also very restricted. So in the literature, there are many advanced models: nested logit, cross-nested logit, generalized nested logit, paired convergence, blah blah blah. Okay. Okay, so this is about the discrete outcome model. So for the quiz, I mean, just two points. Okay, what is the assumption about distribution? Why logit is preferred to the probit? That's all. Okay. And then last issue is about the ordered probability model. So maybe I finish it a little bit earlier today, and then I will briefly review for your preparation of the quiz 1. Okay. So ordered probability model. So now today you learned about the logistic regression and the discrete outcome model, and the last one is the ordered probability. So here, what is the it depends on your y. So ordered probability model means that your indicator y is the ordered. Okay. And then what are the ordered discrete outcome? Order means that order. Okay. Your y become order. What is the order? Like a severity of injury, no injury, minor injury, serious injury, fatality. So as going there, the serious become more serious. And then satisfaction, very dissatisfied, neutral, satisfied, very satisfied. Okay. And the frequency of the use, never, rarely, often, always. So in here, 1, 2, 3, 4, 5. In this, so compared to this one, bus, MTR, taxi, 1, 2, 3. This is the discrete outcome models. But here between 1 to 3, they are no order, right? Larger is not matter of the bigger or smaller, right? But here, if we say for the frequency of the use, 1, 2, 3, 4, 5, then there are some order. Order means that they are not independent. They are correlated. This concept, right? So in this case, we can develop ordered probability model. So Z means that same as a linear regression model, beta x plus epsilon. But here we assume Z is the unobserved, latent, continuous variable. Okay, but it's not unobserved. Then why this order? Order is the Y here. Y. And then Z is a kind of a threshold there. Sorry. Like this. So therefore, Z, we assume the value Z, beta x plus epsilon, is a kind of a threshold. And then Y we can observe. This is the concept. So here Y equal to 0 by convention, no loss of the generality, something blah blah blah. And then so here is the probit and logit, and then logit here is assume the standard logistic distribution, but it's okay. I mean, just for that. And then for the expression probability. So here, probability in the models, probability itself means that CDF. Okay. So in this distribution, let's assume this is the probit. Okay. Then P1, what it means? P1 means that the beta minus beta x, just for example, here, this area is the P y equal 1 in ordered probability model, normal ordered probing model. And then Py2, this area. Therefore, CDF, this one minus this one. Okay. 3, 4, 5, blah, blah. So it's a whole thing about the CDF. Okay. And then in this case, generalized form, this one. Okay. And of course, ordered logit is a assumed logistic distribution, not Campbell distribution here. And then this one is the probability expression. And then this is the CDF of the logistic distribution, and this is the closed form. So still, ordered logit has a closed form, but ordered probit has an open form. But compared to the, how to say, compared to the discrete outcome models, in ordered probability model, this one, CDF minus CDF, is not much difficult to be calculated. So in the ordered probability model, probit is more preferred to the logit. Why? In the logistic model, in the discrete outcome models here, this is the only matter of a single CDF. So it's, I mean, the minus integral is a very big problem. But here, you can imagine here, so form is that this one minus by this one. So for instance, for this area, we calculate this one first and minus by this one. So minus something. So this closed form can be counted, cancel out. So it's more easier to be calculated. Not easy, but it's okay in software. But discrete outcome models is impossible. Okay. So that's only the difference between the probit and logit. in there. So here, where this logic? Where's the velocity? I mentioned here. So here, sorry, maybe I write down somewhere. But anyway, so here, ordered outcome model. Probit is more useful than logit model. Okay. And the others, so what is the point here? I mean, what you should remember. I mean, others, I mean, just a general mathematical model. So you can, if you want to study, you can study more by yourself. I mean, I will just introduce the name and the simple assumptions there. But here, empirically, if you want to apply in your data analysis, a challenge is here. Interpretation, ordered logit model is not clear. Why? Because let's assume that two cases. Let's think about this case. So here, let's assume one is changing. One from the two. Then again, the probability model in the statistics, probability always is about the CDM. So this is the probability for y equal 1. And then this is the probability for the y equal 2. So let's assume what is the larger beta. So when you interpret your result, you maybe for the one variable, beta k equal 1, first variable, second variable 2. So what is the difference between that? It means that, so as shown, here, more beta. When beta is increasing, higher probability. Y1 minus we have 3. Y1, Y2, Y3. So as beta increasing, the threshold will be moved left side. Because minus beta. This one is also moving left side. Because beta is increasing. So here, what is the clear? The area for the y equal 1. Fiercely decreasing. Right? Beta become close to here. The CDF will be increasing left side. It moves to the left side. So compared to here, the area is decreasing. So CDF is decreasing. Here and here. Maybe. So we say, I mean, this one was the original beta. Okay, beta equal 1. And then this is the probability for the P equal Y equal 1, this area, right? And then now, as beta is increasing, now the area is moving here because beta is the positive value. And then now, probably the area is decreasing. Therefore, CDF is decreasing. So probability is decreasing. So it means that for the positive beta means so for the positive beta, lower probability for the strongly disagree. Y equal 1. Why? Because the beta is the area is decreasing. But especially for the largest one, strongly agree. Is it if it is going to left side, then area become wider. Then probability will be higher. Is it understandable? Right? So this one is very clear graphically in this graph, very, very clear. But point is that you can see less focusing on the y equals 3, the neutral. So this is the original area. Right? And then this one is the later one. X is become left. Then problem is that we don't know which one is bigger or smaller. Right? So my point here is that, I mean, for the y equal 1 and y equal 5, the change is clear. As beta is increasing, the probability is y1 will be decreasing. And probability is for the y equal 5 is increasing. So this is the clear. A point for this middle category. We don't know what happened there. We cannot interpret it. Okay. So in this case, the ordered probit, ordered logit, whatever interpretation beta is not clear. So this is the limitation of the ordered probability models. So what is the solution then in reality in your research if you want to use the ordered logit model after estimation of beta? I mean, normally, I mean, the data analysis, after we analyze your data based on some statistical or probability model, we should interpret the result. But in the ordered case, beta interpretation of beta is not clear. So in this case, we normally use the marginal effect. Okay? So marginal effect, I mean, I already explained several times. So I mean, blah, blah, blah. So marginal effect, then largest absolute value, strong influencing ranking, and the positive increased probability of that category, and the negative, it decreased probability of that category. So this is the general way how academic papers using the ordered logit or ordered probit model. Okay. And then I also have an issue, the correlation issue, but maybe it's not difficult. So normally, I mean, so I want to analyze my data, and then actually, I mean, not only for the ordered model, any statistical modeling, you have learned this class, like a regression model or more discrete outcome models or some count data model, whatever. So what is the advanced issue is that we increase more error. So far, I mean, what you have learned is that more space. Here, every model you have learned in my class is that y equal something beta x plus epsilon, always within this formulation. Of course, y is different, so definition of y become more and more complex, right? But anyway, what is the common things? All the models you learned so far, single error. It can be normal, Campbell, whatever, only single error. But in your, if you look at the papers in Q1 journal, I mean, this simple formulation is not appeal because it's already too general. Everyone can use it. Then what, I mean, so normally, if your focus is the data analysis, then what you need to do, you should make a code by yourself for the more complex situation, more complex modeling. So what is the general technique? Adding error, one more error, something like that. Error term, more. And then, I mean, this case, I mean, I explained about the individual specific term, but it can be, of course, I mean, the extended, anything, correlation between y values or whatever. So maybe explain this part maybe too complex, maybe. Okay, so I mean, that's just one key idea. Okay, so any questions so far? These models are too difficult. How do you think? It's new, ordered logic, something like that. Did you hear first time? Okay. Okay, I see. Okay, then, I mean, for the ordered model, what you should remember, okay, so other things, okay. Probit is preferred to logit. Probit is more preferred in the ordered model, but the discrete outcome, logit is more preferred. I can ask you OX, right? So discrete outcome models here, logit is more preferred for the discrete outcome. Why? Probit has some computational issue, but ordered probability models, probit is more preferred to the logit. Why? Because the computational issue is now is okay. Then again, why researchers more prefer assume to be normal distribution for the error term than other distribution? We have lots of distribution. So in week 1, I explained, I mean, maybe from now, I mean, let's review one by one. So this is the first lecture 5. So here in the middle of lecture, so here, I mean, it's not all. I mean, my point is that it's not all. But still, people, they prefer to assume errors follow the normal distribution. Why? Then your answer should be about central limit theorem. Okay, central limit theorem, I lecture. I explained it before. Somewhere here. Sorry. Okay. Here. Central limit theorem. Okay, if there are so many observations, then the distribution of the observations should follow a certain normal distribution. This is the key idea. Okay, that's only the 2 points today. Okay, others, I mean, the mathematics, I will not ask you. Maybe I can give you some like a homework, some basic table. Then I will ask you some basic question. Okay, and then others in the quiz will be about where it is. Short to answer question like that. I mean, so okay, is it is it correct or not? Okay. So in the discrete outcome models, discrete outcome probability model, probing model is more preferred to the logit. Is it okay or not? Is it right or not? No. Okay, something like that. I mean, not complex. Okay. So let's return for the first lecture one by one. So first, sorry. So actually, first lecture is just overview. So maybe not many problem about the quiz from here. It's very specific. Okay, so here to here, distribution and the z value. I mean, obviously you learned about this, right? It's a high school issue, high school mathematics. And then if I use any, I mean, any t-test or some, if you need a normal table, whatever, I will provide everything. Okay. So not difficulty. Difficulty is not my issue. Okay. And then here, I emphasize it, the significance level for the 95% t-value criteria 1.96. Right? You remember my first lecture. Okay. So that's one point. And then mostly, I mean, the quiz will be based on the lecture 2 and lecture 3 about the regression model, basically. Okay. So more like lecture 2. I didn't make the quiz yet, but here, I mean, always issue, we need to get the unbiased parameter from the statistical modeling. Why? Because we use the sample data, not the global data. No one can get the global data, true data. Okay? True data means that all observation for the every possible cases, but it's not possible. And then regression model, something blah blah blah, and then something why to use the regression model, blah blah blah. So obviously, this is the very important major assumption you should remember, right? So, I mean, what is the major, I can ask you, what is the major assumption of the linear regression model? Write the three possible regions, at least three possible regions, three possible assumptions, something like that, right? And then continuous dependent model, blah, blah, blah. And then what is it? And then this is one. And then I repeat several times in the lecture. So here, I forgot where this exactly. OLS estimator is more preferred to the MLE estimator. Why? So normally, I mean, the MLE estimator is more preferred. You can see, I mean, any other model, except for the simple linear regression model, we normally use the MLE. MLE is always basic. But the linear regression model, people normally, I mean, starting point is the OLS rather than MLE. Why? So I show you, I mean, where this MLE estimator. Sorry, I forgot where is the location there. Oh, because the mean in MLE estimator, the mean is unbiased. We can derive it mathematically, but the variance of the beta, the standard error of the beta, can be biased. So, here. So for the both MLE and OLS, the mean of the beta, expected value of the beta, both of them is unbiased, right? But for the MLE, for the variance of the standard error of the beta, can be biased. But of course, if the sample is very, very, very large, then they are no bias for the variance of the beta. But otherwise, in MLE, if your sample size is not big, not infinity, then it's biased. So, but in the OLS estimator, variance is not necessary. why they strictly assume IID normal, only IID normal there. Okay, so OLS estimator only mean is expected value, mean is necessary. So OLS estimator mean is unbiased mathematically. You don't need to remember derivation, but you should remember the reason. Okay, that's the key point. And then others are quite general. Then the standardized coefficient. I can ask you why we need to use a standardized coefficient instead of coefficient. Here, for the interpretation, I have this value, but why I need this value? Right? So I explained several times in the lecture, right? And transformation is so why we need to use a Box-Cox transformation? Something like that. I lectured about Box-Cox transformation. Maybe it should be in lecture 2 or lecture 3. Maybe in lecture 3. Box-Cox transformation is the title of the subsection, right? So why we need to use it? For the nonlinear relationship. And lecture 3. Sorry. Quiz others. Other questions will be similar to the homework 1, very basic level. You check the homework 1, right? And then others, I made some to distinguish your score. I make some critical problem like this. Something like so far. I will ask you directly. Okay, why Box-Cox transformation is necessary? And then in the lecture 3, I also lecture about the Tobin model. Right? You don't need to remember about the mathematical expression about Tobin model, but at least you should remember what is the Tobin model, why we need it, right? So, so before go to the Tobin model, here, goodness of fit. I lectured about goodness of fit for the regression model. It's quite general. For the every model. So I lectured about low square and the adjusted low square, right? So we have a low square, but why we need the adjusted low square, right? I explain, and then it is in the lecture file, right? So I can ask you why researchers prefer adjusted low square instead of the low square, and then I will ask you write down the answer. Okay. Then SST, SSL is okay. And what else? Multicollinearity. So of course, I can also ask multicollinearity. What it means? What it means the multicollinearity in the regression model? Very simple, right? But you should write down the answer. Such level, okay? What is the multicollinearity? X are correlated. Okay. So X1, X2 are correlated. This is the multicollinearity. Okay, X attribute X are correlated, very complexly correlated. So here. Okay. So high correlated independent variables correlate is X multiple X's are correlated to each other. It's called the multicollinearity. Okay. So what else? What else? Stepwise regression, tree-based approach. Maybe too difficult. Yeah. Also, elasticities. Many appear this lecture, right? Today I also explain about elasticity. I can ask you, what is the elasticity? What is the definition of the elasticity? Formula, no formula. Okay, the concept. So Tobin model, I mean, so why we need a Tobin model? Okay. So for the Tobin model, which estimator is more preferred, OLS or MLE? I can ask you. And why? So I talk about this many times, right? MLE is more preferred. Why? Because OLS strictly assume errors are IID normal. But in this Tobin figure, I mean, especially this part and this part, they should be non-identical, of course. So IID normal assumption in OLS is not difficult to be defended in the Tobin model. So MLE is more preferred. Always same discrete outcome model. Why MLE? IID normal in OLS is not easy to be defended. So normally OLS estimator only used in the linear regression model. Function, Box-Cox transformation. What is the Box-Cox transformation? Something like that. Simultaneous equation model, I remember you don't, so it's okay. Okay, and the lecture file and the latent variable. So once you prepare your quiz, what is my suggestion is that, I mean, for each there, I mean, I have titles there, right? So at least you understand why the title is important. The title normally is about the model. Okay. For instance, no, it's okay. So structured data here, latent variable model. So example, latent variable and the factor analysis, principal component analysis, and the factor analysis, and the structural equation modeling. Okay, so something blah, 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 and how to clustering is about the clustering. And here, so here, I emphasize it in the lecture file here. So in this figure, how many cluster? You should know, okay? I mean, check the lecture video again. The eigen, based on the eigen value, how we decide in the number of the principal components, something like that. Okay. Vector analysis, something blah blah blah, and then so types of the factor solutions, orthogonal factors, obliquely correlated factors. So I can ask you, okay, this figure, this is what I want to analyze it. Which one? Which analysis here? This is the orthogonal factor analysis, or this is the oblique factor analysis? I also explain it during lecture. Very simple, right? It's a matter of the ONX. Okay, and interpretation, blah, blah, blah. And then structural equation modeling is a core. SEM is the independent variable, and one more dependent variable. Multiple Y can be possible in the structural equation modeling. And the different direction there, path analysis, I explain what is there, blah, blah, blah. Causality issue there, path analysis. And then here, exogenous, and so, I mean, without, I mean, this, so here, I can show you like this, and then I can ask you, what is the endogenous variables here? Okay, something like that. You need to write which one is the endogenous or anything, which one is exogenous, or okay. I mean, this point, I mean, I already explained during my lecture. So if you do not know the answer correctly, I mean, find the lecture video again. Okay. So exogenous y and endogenous is exogenous x is endogenous is y. So here we have a 2y here. Okay. And then here, SCM constructing, Russell, and blah, blah, blah. And then blah, 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 and the model specification, and here, okay, here, 0, 0, 0, 0, 0, 0. So I can show you this equation. Okay, this is my formulation in the SEM modeling, especially for the path analysis part. The path analysis part, so this one similarly, and no, not this one. Model specification, something blah blah blah. Okay, necessary condition, sufficient condition. Maybe it's okay. It's too deep. It's too complex. Okay. No ideal condition. So also, of course, I can ask you for the SEM in terms of the distribution, error distribution. In terms of the distribution of the observation, what is the ideal condition? You say, oh, multivariated normality. It means that, the observation of variable is a normal distribution. I also explain it during the lecture. All the variable, normal. So multivariate. Multivariate is that multivariables. Normality, normal distribution. Something blah blah blah. Okay, that's all. And then the last one is the today lecture. So I already told you about the point, right? But that's all. Quiz will be like this level. Okay, not much difficult. But it's more about conceptual questions. So you should remember some fundamental ideas about the contents in this lecture. That's all. Equation mathematics will not be much complex. Okay, but bring your calculator. Okay. Any question? So week 7, I briefly talk about 1 hour lecture. It's about another advanced model, continuous discrete outcome model, mixture of the model as a last topic. And then it will not be in the quiz 1, of course. Quiz 1 will be until lecture 5. That's all. Okay. So if you don't have any question, I have a question to you. So maybe this lecture biannual. So 2 years later, I will lecture this class again. So do you have any suggestions? So because for me as a lecturer, what is the difficulty is that I don't know your level correctly. So because this is the PhD level open course. If it is only for my major, I can make more focus. It's easier. But now you have from different department and then you have a different topic. So as a lecturer, it is very difficult for us. What is your focus and what you are interested? So how can I make it general? And then do you have any suggestion for the next lecture for me? 2 years later. So first idea, within our department was that make it more higher level for the PhD students for their PhD work. But now I realize that it's not always for you. So any suggestion, any issue, any suggestion, any idea, any feedback? Yes. Actually, this is based on our CEE program. So actually, our focus was about the CEE students, and then maybe some more students from the FCE. But now, even within FCE, not many students from there. So maybe I need to make it more general next time, maybe. So, but the focus was that the higher mathematical knowledge for the students. because normally, especially in CEE in our department, we require some more and more mathematics for their and to ask them to analyze their data. So so for me, my part, I mean, is almost done, so it's okay. But I should tell you, maybe the second part will be more difficult, more mathematics in terms of the machine learning. So, but it's out of my authority. My part is until the week 6.
Level of detail is like, give us a general idea of which assumption is suitable for this situation. And for those math details, it's
Maybe not useful.
maybe now error.
Yeah.
Yeah.
Okay, I see. Okay.
Another suggestion is that I took a simulation course
Ah.
among MCB students last term, and the lecturer there he just gave us some more specific like engineering background, for example, some cases, and use these cases. For example, in that course is earth moving, a very basic construction process. Use this case all along the case, all along the course to demonstrate some of the models, some of the philosophies behind it. So in your case, probably some very simple transportation case and elaborate it
Okay.
along the way.
Okay, I see. Okay. Yes. Any other suggestion also? Mm. Yes.
That's something I'm from.
Yes.
I'll just generally problem.
Okay.
However, just like what like this course, what do we do some calculation? Why we do this? I mean, please leave without calculating. Even things will come.
Okay. Okay, I see. Okay. Oh, yes, I got the point. Okay. So any other feedback or comments? Okay, then that's all. So happy Chinese New Year. Okay.